Hi guys, so in this video we are going to deliberate on the concept of wedges. Okay, apa tu wedges? Potato wedges ke? So wedges is actually a kind of triangular feature used to raise or lift some heavy object. It is even used to assist for the process of splitting the object. Okay, sometimes the wedges are used to hold an object in place. Okay. The structural feature of wedges is so special is that it can transform a small load into a much larger force, so that is why lifting a heavy object is possible. Okay, so the mechanical study in wedges definitely involve the concept of dry friction between two different contact surfaces. The first contact surface involves a contact with the floor. Okay, and the second contact surface involve a contact with the object itself. So now let us see how we can construct the free body diagram of the multiple components involving wedges. Now consider an object with the weight acting at the centroid of the object. Okay, this object is resting against two surfaces, which is the floor and the wall. So now a wedge is being inserted in between the object and the floor to lift it to a certain height. Okay, so a small force P is used to lift the object with the weight of W using a wedge with an angle of theta. Now let us draw the free body diagram of the wedge first. Okay, so this is the same profile of the wedge as shown in the figure on the left. Okay, and the P is actually the pushing force which pushes the wedge in between the object and the floor. Okay, the wedge is touching with the floor. So by right, when it is being inserted in between the floor and also the object, then there is a frictional force acting at that particular contact surface. So by right, there is one friction force over here in the opposite direction of the motion of the wedge, and there is a reactive normal force at the contact surface to counteract the weight of the object. Okay, sama je macam the concept of friction sebelum ni. Okay, this wedge is also in contact with the circular object. So by right, there is a normal force acting downward perpendicular to the surface of the wedge. Okay, and by right, there is also a frictional force acting in this direction, and we're going to call it F2. So let's not forget the free body diagram of the object itself. Okay, so this is a circular object with weight acting on the centroid of the object. So this object again is touching with the wedge at the inclined surface. So the direction of the force would be in the opposite direction to the force on the wedge. It's like a couple force lah. So if N2 at the wedge is pointed downward, so the N2 at the object will be pointed upward. Accordingly, the friction, if the friction at the wedge is pointed to the left, then the friction at the object will be pointed to the right. Okay, now this object is also touching with the vertical wall. So at any point that it is touching, then definitely there would be a normal force acting on the direction perpendicular to the surface. And accordingly, there is also a friction force which is in the downward direction like this. Okay? So this is the ideal free body diagram for both of the wedges and also the object that it is holding on. An important indicator when it comes to the magnitude of the pushing force of a wedge is that if the magnitude of the P is positive, then the wedge must be pulled out, okay, immediately. Okay, and if the P is 0, then the wedge will stay in its place, or we call it self-locking mechanism. Okay, if the P is negative, then it is likely that the wedge will come out on its own. Okay, so that are three important criteria on the magnitudes of P in the case of wedges. In solving the mechanical problem like this, it is most ideal if we can come up with the free body diagram of the components that we want to study. So in this case, we are going to draw the free body diagram of the object, which is a stone, as well as the free body diagram of the wedge. Okay, so this is, let me just resketch the diagram of the stone, and given in the question that the stone has a mass of 500 kilogram. So if we convert that mass into equivalent weight, so 500 multiplied with the gravitational acceleration of 9.81, we'll get the magnitude of the weight to be 4,905 Newton. Okay, so the weight will be acting at the centroid of the object. So in other words, if the length of the stone is 1 meter, so the weight will act at 0.5 meter from the left and also 0.5 meter to the right. Okay, now also given in the question that it is held in horizontal position using a wedge at B. So the wedge is in contact with the stone. So there would be a normal force acting perpendicular to the surface of the wedge. And there will also be a frictional force over here. We'll call it FP. So now, probably if it slip, then the motion will be in this particular direction, downward, kan? So therefore, the direction of the friction would be in the upward direction, the inclined upward direction. Let us redraw the resultant normal force and also the friction force on our free body diagram. So the question asks you to find the minimum force P required to remove the wedge. So if you want to remove the wedge, it means that slip occurs between the stone and also the wedge. So therefore, if slip occurs, then we can redefine the friction force at point B to be the friction limit formula, which is mu n. Okay, so the mu is already given to be 0.3, and the n that we are going to use is the normal force at point B and B. Okay, also given in the question is that we assume that the stone does not slip at A. The stone is also touching at point A, kan? So there is also a resultant normal force at point A, and there is also a potential frictional force at point A as well. Probably it will move in this direction, so the direction of the force will be in the opposite direction. But it does not slip, so we cannot simply define the friction at point A to be mu n like we define in FP. Cannot, okay? So now let us draw the free body diagram of the wedge itself. So the wedge have an inclined angle of 7 degree. Well, I forgot, if this is 7 degree, then the angle over here would also be 7 degree. So you know the wedge is touching the object at point B. So if the NB at the object is pointing in this direction, so the NB on the surface of the wedge would be on the other direction with the same magnitude. Okay, accordingly the friction at point B would also be in the opposite direction of the one defined in the object. So again, we know that FB is equivalent to 0.3 NB. This wedge is also in contact with the floor at point C. So accordingly, there will be a resultant normal force at point C, we call it NC, and there is also a frictional force at point C in this particular direction. As described in the question, we need to remove the wedge. So if we need to remove the wedge, then the friction force at the floor should also be the value of the friction limit, which is mu n. So in this case, we can substitute the value of Fc to be equivalent to 0.3 nc. Before we can construct the equation of equilibrium, so we first need to define all the senget-benget forces into an equivalent x and y direction. Okay, so if you look at the free body diagram of the object or the stone, you'll notice that the direction of normal force B is inclined at 7 degree. So we can convert it into an equivalent y direction. So this would become NB cos 7, and along the x direction, the magnitude will become NB sin 7. Accordingly, the magnitude of FB can also be resolved into the x and y direction. So in the x direction, it will become 0.3 NB multiplied with cos 7, because this would be 7 degree. And along the y direction, the magnitude would become 0.3 NB sin 7. Now we can apply the equation of equilibrium on our first free body diagram. Okay, so since we are more interested to get the value of forces at the wedges, so the only way for us to get that forces is by eliminating the force at point A. Okay, because we are more interested at point B though. So therefore, in order to do that, the only way to do that is actually to apply the equilibrium condition for moment at point A, so that we can cancel out all the forces which passes through point A. Okay, so that is the interesting part of the equilibrium condition. Okay, now applying the moment at point A, so the force of 4905 Newton will create a moment at a distance of 0.5 meter, and the direction of this force will create a clockwise moment, so it will be a negative value. And then accordingly, this force of NB cos 7 will also create moment at a distance of 1 meter. The direction of the moment will be counterclockwise, it will be positive. And ada lagi tak? Okay, this NB sin 7 tak ada moment, it will not create moment because the line of force passes through the rotation point A. similar with this 0.3 NB cos 7. Okay, this 0.3 NB sin 7, definitely there will be a moment acting at a distance of 1 meter. And the direction of the moment caused by this force would be counterclockwise. So the magnitude of this element will be positive. Okay, so that is all, I think. So the summation of all these three elements would sums up to 0. Okay, so let's just rearrange our equation so that the unknown of NB to be at one side. So that is NB cos 7 plus 0.3 NB sin 7, and that sums up to the multiplication of 4905 with 0.5. So you get 2452.5. Okay, so you can actually factor out the unknown NB like this. So the unknown NB is being factored out, and the remaining magnitude will be cos 7 plus 0.3 sin 7. Okay, that will be equivalent to 2452.5. Okay, I'm going to continue this over here because my worksheet is not enough. So therefore, I can easily solve for NB by dividing the 2452.5 with the expression of cos 7 plus 0.3 sin 7. So I will get the magnitude of the normal force at point B to be 2383.13 Newton. Okay, cool. Now we can use the magnitude of NB that we get in the free body diagram of the wedge. We can now proceed the analysis by considering the free body diagram of the wedge. Okay, before we proceed, let us identify all the senget-benget forces, all the inclined forces, and redefine it into an equivalent x and y direction. We can resolve the incline NB into an equivalent y direction, and the magnitude, okay, the angle is 7 degrees, so the magnitude become NB cos 7, and accordingly, if it is being resolved in the x direction, it will become NB sin 7. Okay, accordingly, the inclined line of force of FB can also be resolved into an equivalent x direction, whereby it becomes 0.3 NB cos 7 degree, and along the y direction, it becomes 0.3 NB sin 7 degree. Okay, now we can apply the equilibrium condition. Let's start from the y direction. Okay, so there are three forces acting in the y direction, which is the NB cos 7, and then this 0.3 NB sin 7, and also this NC. Okay, there are three items over here that sums up to 0. So recall that we already calculated NB earlier, which is the 2383 Newton, kan? So we just substitute that value into our equation, and it will become like this. So in the equation, there remains only one value of unknown, which is the NC. You can easily solve for NC and calculate it on your own, and you'll get a value of 2452.5 Newton. Okay, so now we can apply the equilibrium condition in the x direction. Okay, so I think there are four items in the x direction, which is this NB sin 7, and this 0.3 NC, and this 0.3 NB cos 7, and also this P. Okay, so you include all that four items into your equation of equilibrium in the x direction, and all the elements sums up to 0. Okay, so recall that we already calculated NB earlier, the 2383 Newton, and we already got the value for NC as well, which is the 2452 Newton. So what's left is only one unknown lah, which is the P value, the item that we want to calculate. So you just substitute the known value into the equation, and conveniently, you can easily solve for the P value, and the magnitude of P will be 1154.93 Newton. Okay, so based from this answer, you can see that the magnitude of the P that you get is positive. Okay, remember the criteria described earlier in the earlier part of this lecture series. So if P is positive, the wedge must be pulled out. It fits the criteria as described in the question above. Okay, so dah siap. Okay, now let us look at this quite interesting example. Okay, the load is being subjected onto two wedges with the smooth roller placed in between them. Oh, sudah. So, banyak ke normal force and friction force yang kita kena calculate? Tidak semestinya. Let's look at the information given in the question. We know that the load have a weight of 100 Newton, so the W is acting downward at its centroid, and the mu between surface AC, the surface which contacts something else, which is surface A and surface C, and also surface B and surface D, is 0.3. Okay. Based from this statement, we can consider that surface AC and surface BD is the particular surface where friction will occur. So we need to consider the resultant normal and friction force in our free body diagram. Okay, so the other information given in the question is that smooth roller placed between wedges A and B, and we just assume that the roller and wedges have negligible weight. Okay, so we don't have to consider the weight of these two wedges and also the four rollers. Okay, the question wants you to find the force P needed to lift the load. Okay, so as always, the first step in any kind of problem involving wedges is to draw the free body diagram of the wedges itself. So let's call this wedge to be wedge X and this one to be wedge Y. Okay, now we are going to draw the free body diagram of wedge X and also wedge Y. So at wedge X, okay, there is a contact area at point D. Okay, when there is a contact area over there, then there is a resultant normal force acting at that particular direction. So I'm going to call this N1. Accordingly, there will be a resultant friction force acting downward because they are lifting the load, kan? So if it is lifting the load, then the motion is pointed upward. So therefore the friction try to resist the motion, so the friction would be pointed downward. So we're going to call this FD. Okay, so we know the weight of the load are being subjected to the wedge. So if we project this line further until it reaches the contact point of the wedge, so there would be a W pointed downward with a magnitude of 100 Newton over here. Okay, now look carefully. Surface B are in contact with the smooth roller. Okay, at any point where contact exists between two bodies, then definitely there would be a normal force acting perpendicular to the surface of the contact. So in this case, if there are four rollers, it is not necessary that you include the normal force at every single roller. No need. You can actually represent the normal force which represent the contact between the roller and also the wedge with only a single normal force like this. Okay, so we are going to call this normal force as N2. Okay, will there be any friction at the contact between the smooth roller and the wedges? Okay, here's a hint. Every time you see the word smooth, it means that friction will not exist at that particular contact surface. Okay, so therefore there is no resultant friction happening along surface B. Now that's done, let us draw the free body diagram of wedge Y. Okay, so at this particular point, point A, there is a resultant normal force acting perpendicular to the contact surface. Okay, the magnitude of the normal force would be N2 because it's just a roller. So that is why the magnitude acting at B and also the normal force acting at A have the same magnitude, just that it have a different direction. Okay, it's just like a couple force. Alright, now there is also a pushing force acting at this particular direction, and accordingly, if you look carefully, this wedge is touching with the floor at point C. So if it is touching, then definitely there would be a friction and a resultant normal force over there. So there would be one normal force, we'll call it N3 over here, and if this wedge is being pulled inward, so therefore the direction of friction force at point C will be in the opposite direction, which is this way. Based from this question, we know that the pushing force are exerting a force which requires a movement so that the load are being lifted. Okay, so every time there's movement, it means that slipping happen, and if slipping happen, then at any area where friction happen, then you can use the formula of the friction limit, which is mu n. So mu is already given, which is 0.3. So at any point where friction happen, you can use the formula of 0.3 multiplied with its respective normal force. Okay, looking back to our free body diagram, the first friction at point D can also be represented with 0.3 and 1, and the second friction at point C can also be represented with 0.3 multiplied with N3. Okay, based on the free body diagram that we constructed earlier, there are 4 unknowns in that system, okay, which is N1, N2, N3, and also the magnitude of P, force P. So all these 4 unknowns needs to be solved with 4 equations of equilibrium. Okay, now let's try to do this on our own. Okay, let us first consider for wedge X. Let's apply the equilibrium condition in the X direction first. Oh dear, I just realized that the N2 is subjected to an inclined surface. So more or less you need to resolve the N2 into an equivalent X and Y direction. Okay, now you know the angle over here is 10 degree. So this angle will also be 10 degree. So this N2, if it is being resolved in the Y direction, it will become N2 cos 10. And if it is being resolved in the X direction, it will become N2 sine 10. Okay, now that is complete. Okay, let's just resolve the N2 at wedge Y. Siap-siap, okay? So, again, the angle is 10 degree. So, the N2 can be resolved in the Y direction to become N2 cos 10. And it can also be resolved in the X direction to become N2 sine 10. Now, let's go back to wedge X. If we apply the equilibrium condition in the X direction, okay, so there are 2 elements in the X direction, which is the N2 sine 10 and also the N1. So you just put that into your equation and that sums up to 0. So there are 2 unknowns here. You can't really solve it yet. So let's just call this equation to be equation number 1. Okay, accordingly, if we apply equilibrium condition in the Y direction, okay, you put all the forces acting in the Y direction, which is this 100 and this N2 cos 10 and also this 0.3 N1. So you put that into your equation and that sums up to 0. So if I were to rearrange this equation and we put all the unknowns at one side, which is the left side, so I can rewrite this equation as N2 cos 10 minus 0.3 N1 equivalent to, okay, negative 100, bawa ke kanan, it will become 100. Okay, this would be equation 2. So, if you compare between equation 1 and equation 2, it is actually a kind of simultaneous equation. Cool. So, if this is a simultaneous equation with the same unknown variable, which is N2 and N1, then you can solve this equation 1 and 2 simply by using the calculator. Senang. So, sine 10 would be the value of your A1, B1 would be negative 1, and the value of C1 would be 0, and A2 will be cos 10, B2 would be negative 0.3, and the C2 would be 100. So, tekan calculator. At the end of the day, you will get the magnitude of N2 to be 107.21 Newton, and the magnitude of N1 to be 18.62 Newton. Cool. So, now let us calculate the remaining unknowns by considering wedge Y. Okay, I want to redraw the diagram of wedge Y over here with all its corresponding forces so that I don't have to scroll back and forth to the original diagram. Okay, so this is wedge Y. Now, let's apply the equilibrium condition in the Y direction first, okay? So, there are 2 items in the Y direction, which is the N3 and also the N2 cos 10. Put that into your equation, sum it up to 0. And then, recall that you already calculated N2 earlier, kan? From the wedge X in your problem. So, you just substitute the value of N2 to be 107.21. So, there will be only one unknown left, which is the N3. So, that N3, if you calculate it, it will sum up to 105.58 Newton. Okay, done. One more variable, which is the P that we want. Okay, so let us apply the equilibrium condition in the X direction pula. Okay, so that is the P, the golden P that we want to look for, and also that is the N2 sine 10, and also that is the 0.3 and 3. So that sums up to 0. So recall N2 you already calculated from the wedge X calculation, which is 107 Newton, and N3 is the value that you just get just now, which is 105.58 Newton. So you put all that known values into the equation, and at the end of the day, you can get the value of P, and the magnitude is 50.29 Newton. Finally, dah siap. Okay, so that is all on friction and wedges. Okay, I hope you enjoyed the lecture series. So in the next video, we are going to look into the final chapter of statics, which is centroid and composite body. It's a very interesting and very simple concept. Okay, till then, see you later, alligator.